Welcome, scholars, back to Mr. Honeycutt's math class. Now we're working on finding horizontal asymptotes. They're quite a bit different from vertical asymptotes. So in the real world, horizontal asymptotes are going to tell us kind of when mathematical models settle down or they reach some sort of equilibrium. So again, looking at some of the COVID stuff. So notice like here's some curves, here's the United States, things like that. Notice here's China. And notice it started to reach kind of a flat line that looks like a horizontal asymptote where like their level of cases seems to be leveling off. I don't know what that is now, but like this is kind of a horizontal asymptote. They've reached some sort of equilibrium. They've kind of figured out how to fight the virus. It's reached some sort of constant level. Okay, and that's kind of how horizontal asymptotes work in the real world and how we would use them. Getting to the math, I just want to review real quick that y-intercepts caused by inputting 0 into a function, x-intercepts by a function outputting a 0 or multiplying by 0. And then we learned that vertical asymptotes are caused by a function dividing by 0. All right, dividing by 0. Or we could also think of that as outputting infinity if you want. Okay, and so one way to think about what's happening with horizontal asymptotes is they're caused by inputting the reciprocal of 0 into a function, by inputting infinity. So if the vertical asymptotes output infinity, horizontal asymptotes input infinity. Hey, that's really similar to y-intercepts and x-intercepts. Why, yes, it is. So why this actually works and how these kind of laws work about how horizontal asymptotes work is I want you to kind of think through like what happens as numbers grow larger and larger. So we're going to start with some simple stuff. So we're going to start with this function f here, x plus 5. G of x is x to the third plus 3. And then h of x is f over g. Okay, and you need some sort of model here of a rate of a function over another function for a horizontal asymptote to happen. Okay, so if it doesn't have a denominator, it's not gonna really do a horizontal asymptote, unless of course you have exponentials, and they do have horizontal asymptotes. So notice though, and then I've got this function that h approximates. And what I want you to see, and what we're gonna see, so let's just do these. So 0 plus 5, okay, and then this is 0 cubed plus 4, all right, and then putting those together, that's 5 over 4. However, if I plug this in, this would be 1 over 0. That doesn't really work. Okay. All right, so notice, and then now we're going to do 1 plus 5. 1 cubed plus 4. This would end up being 6 over 5. And in this case, it would be 1 over 1 squared, plugging this in. And hey, 6 over 5, that's like 1.2. And this is just 1. So these are, in fact, kind of close. These ones weren't, okay, because of the asymptote stuff, the vertical asymptotes. Now, if we do 10 plus 5, that's just going to be 15. And then 10 cubed plus 4. Hey, 10 cubed, that's 1,000. That's going to be 1,004. So then putting these together, that's going to be 15 over 1,004, which is 0.015. Okay. If you do this one, it's going to be 1 over 10 squared. This one right here, which would be 1 over 100, which is 0.01. So notice, hey, we're still pretty close. Closer than we were here, in fact. This one was off by 2/10. Okay, this one is off only by 5 thousandths. Now let's do x equals 1,000. So this would be 1,005. This would be 1,000 cubed plus 4. That's going to be 1,000,000,004. Okay, oh, and that one's a 4. So this would be 1,005 over 1,000,000,000. All right, which ends up being 0.000001, 1 millionth. If you do the same thing over here, the approximation, so it's 1,000 squared, it also ends up being point. Now there's other stuff behind this decimal, but in this one there's not. So, but notice though, they are functionally the same at 1,000. And as the number x gets larger and larger, this simple model is going to show what's happening at the end of that behavior, like the limits of it. So basically what that means is that these numbers don't matter in the end. That's what's really important. Once you start, because these get so much bigger than these, that and at infinities at the ends where the horizontal asymptotes are, it's only the variables, the leading coefficient numbers, the leading degree numbers that actually matter, not this stuff, because those end up just not mattering. Notice, like, it just doesn't really matter. I mean, there are some little stuff like farther around, and as the numbers get bigger and bigger, they will matter even less, and these two will get closer and closer together. So there are three possible outcomes. Now, that's the big concept, excuse me. There's three possible outcomes for what can happen when you have this numerator over denominator style function, a top over a bottom. Okay, and one is that the bottom is bigger, the denominator function has a larger exponent or thing that gets to infinity faster. One is that the top is bigger, that means that whatever's on top, whatever function on top is, it gets to infinity faster. And the other option is that the bottom and the top are basically the same. They get to infinity at about the same time and they cancel each other out. So let's go through these outcomes. So the first one, and this is called, the bigger on bottom one is called the Bob-Yo. Okay, as you'll see, this is one way to think about it. The other is the Bot-Na and the Eats DC. These all stand for something. I'll show you what they mean. So let's do the Bob-Yo first. All right, the end behavior of this rational function. So Bob-Yo, all right, means bigger on bottom. All right, Bob. All right, and then the yo is a clever way of thinking. It means y equals 0. So it's not really a yo, it's an o. Okay, so in this scenario, this one is bigger on bottom because the degree of this polynomial in this function is higher than the degree of this one. 3 is more than 2. So it's bigger on bottom, all right? And if you graph it, here's actually what the graph looks like, all right? So, and it looks kind of weird. Here's an asymptote here. There's a vertical asymptote here, and then there's this horizontal asymptote here. Notice there is a horizontal asymptote at y equals 0, which was the x-axis. Okay, that's the x-axis, by the way. Okay, and if there's something bigger on, that means this is going to infinity faster. Okay, so basically this is going to look like 1 over infinity. All right, infinity. All right, as we know, that's like kind of one of our definitions of 0. That's why it becomes 0. All right, so, and then other ways we can talk about that are with limits. The limit as x approaches infinity of f of x, in this case, is 0. That means the limit as we're going this way to the left, that's actually this one. The negative infinity goes this way. The positive infinity one is the limit as it goes this way. These are the same. You actually can have two different horizontal asymptotes. Sometimes you can only have a left-handed asymptote, like with exponentials. But yeah, that's just what the limit notation, when they're talking about limits at infinity, that's basically talking about, are there asymptotes? I mean, there's more to it, but that's one of the ways you can think of it as asymptotes. Let's do the next one. The Bot-Na. All right, that stands for it's big on top. That means there is no asymptote. All right? So, and asymptote in here, they mean no horizontal asymptote. So notice there is a vertical asymptote here, but there's not a horizontal asymptote. So it is bigger on top, all right? This degree is higher than this, and it's not always the leading one, by the way, all right? Sometimes this might be rearranged, but the highest degree is larger on top, bigger on top, okay? And then that's bigger than that. So that means there's no asymptote, all right? And then at that point, this function is just going to, because we're going to ignore this stuff, it simplifies out and it's going to act like negative x for its end behavior. Okay, so it's going to act kind of like negative x. And if you draw a negative x line, which would go right about here, notice that as you get farther away from the weird stuff in the middle, it's acting more and more like negative x. That's a terrible, terrible drawing of negative x. All right, So moving along. This one is probably the most interesting and the most helpful. This is everyone's favorite. Okay, if the exponent, the EATS DC means exponents are the same, EATS, divide the coefficients. If the exponents, the leading exponents, these two exponents are the same, hey, look at that, they are. That means that you can actually not only cancel this out, you can cancel these guys out, and the horizontal asymptote is just going to be the leading coefficients. And we just divide them. So what's the horizontal asymptote? The horizontal asymptote in this case is going to be 3/2, which is about 1.5, and it's right there. And hey, look at that. That's the horizontal asymptote. One thing I want to point out, notice this horizontal asymptote, it actually crosses here and here, the graph. That really freaks some kids out for some reason. Horizontal asymptotes are basically about what's happening at the end. I think in some ways, like some Algebra 2 teachers talk about asymptotes as in like they don't touch. But when it touches there, it's like, oh, okay, yeah, but it's over here. It gets close, but not touches. So yeah, and again, notice the limits. The positive limit in this direction is going to positive 3/2, the negative limit's in 3/2. So the EATS DC, this one's really nice. Once you just notice the pattern here, if it's asking for a horizontal asymptote, you can just divide the coefficients. So here's they all are together. All right, the Bob-Yo, the Bot-Na, the EATS DC. If it's bigger, and again, the basic idea is that in behavior model, the basic idea is at infinity, this stuff's not going to matter. Okay, this stuff's not going to matter. This stuff's not going to matter. All right. The only thing that matters is basically this thing, and in this case, this thing. So it's going to act like those functions, and then you would use exponent rules to kind of simplify those. All right, but then these are the three kinds. The bigger on bottom, Bob-Yo. Bigger on top, Bot-Na. No asymptote. All right, EATS DC, exponents are the same, divide the coefficients here. So yeah, this one it's 0 if it's bigger on bottom. This one you get an actual number or a fraction. And this one there just isn't one. Now, I want to circle back and kind of summarize the entire lesson here. All right, the first thing we talked about was y-intercepts. All right, and y-intercepts are when you input a 0. When you input a 0, that's your initial condition, and whatever it outputs, that's what your y-intercept is. Okay, and x-intercepts are when you output a 0. Okay, that's where it hits the x-axis, and those are roots or solutions, and then there's the 0 product property. Okay, that's when we're multiplying by 0, and there's special features there. Then the horizontal asymptotes are like if the y-intercepts were like when we inputted 0, horizontal asymptotes are when we input 0's reciprocal, which is, hey, infinity, because 1 over 0 is basically infinity. So if I input an infinity, okay, that's where I get my horizontal asymptotes. And now this, by the way, could be a positive or negative infinity, all right? And then over here, vertical asymptotes are kind of in a sense where when the function outputs infinity as opposed to outputting a 0, because we are dividing by where there's a 0 in the denominator. That's what's creating the vertical asymptote. So that's just kind of how it all, notice that these are all connected concepts, but they do have nuances and they could be easy to confuse. So make sure you understand, like, hey, my y-intercept, my initial conditions, I'm inputting a 0. My x-intercept is when I'm outputting a 0. All right, my horizontal asymptotes are when I'm inputting infinity. My vertical asymptotes are when I'm outputting infinity, which is another way of saying I'm dividing by 0. Okay? That's the basic stuff for all of these, and they are all connected. We've covered an enormous amount of material this lesson. I hope you are seeing connections. Hopefully this was all not new, but you're seeing connections between the material that you haven't seen before, and I hope that it helps you conceptually understand this and that you can apply it in new and different ways, especially on the ACT and the IB tests. All right, so start working on that application practice, and yeah. Can we fix everything? No, but we can fix something today.